All right. So kind of ran out of time on the last slide, and so I want to go back and just look at this example just for a minute. Now this is the end of that section, so there was some problems after that to work on. So just a lot going on with this problem. I just want to point out the highlights just one last time. And so when you're looking at this problem, the key thing that will stand out is that you'll have these molarities. And so a problem with two molarities is going to be kind of suspicious. So the molarities will also be the same molarity. You won't ever have anything where they're different because you can't figure out the moles at that point. So they have to be the same. So that's a good I guess hint. So the second thing is that this is an acid base problem, as I pointed out here. So the things that start with the H, like that, those are acids, and things that have an OH at the end, those are the bases. And I don't know if I did a great job of explaining that, but since it's an acid base, that's what led us to this final idea that the delta H had to be negative. And so you kind of have to understand that and make the final answer negative. So remember, combustion and acid base are always going to have a negative delta H answer. All right. So then the other pitfalls that students run into on this problem, and it is a hard problem, other pitfalls they run into is the mass, because they're not given any mass. And so a lot of times students really struggle with that concept. And so that's where that density of water comes in, that since we know the density of water is 1, then we can just say 1 equals x over volume. And since we have volume, we can get that figured out. Well, also, a thing that's a little confusing to students is the unit for density is grams per milliliter. So that means the milliliters really work out quite well to get your mass value. Then you just kind of run it through, making sure that you understand how to find temperature, final minus initial, and you end up getting an answer, and then that answer being in joules, that can be a bit of a problem because delta H is not in joules. And so remembering that delta H is supposed to be kilojoules per mole, then we found the moles, took the kilojoules, divided by the moles. And so one of the main things walking away from this problem that will help you is to understand that delta H is really just how many kilojoules you have divided by how many moles you have. And so it's a little more complicated because it's based upon the balanced equation, but moles are always related to delta H. It's not just a kilojoule or a joule value. So anyway, just some small things, pretty complicated problem. I might put one like this on the test. If I did, it would be definitely one of the hardest problems on the test. So, all right, so let's take a look at the next piece. The next piece is Hess's law. So first of all, this is a guaranteed test question every single year. And I don't just mean on my test, I mean on the actual IB exam. Okay, why is that? Well, they devote an entire section of the curriculum to one thing, Hess's law. So a single item is going to be an entire section. And so we're going to work through this section, and then we're going to do some practice problems. And so that's kind of what we'll do here. So first of all, I need a definition for Hess's law. And so what Hess's law is saying is that if you solve a problem with one step, or if you solve a problem with multiple steps, your answer at the end for delta H is going to be the same. So if you might recall, I said that a lot of this unit is just different ways to find delta H. Well, Hess's law is just another way to find delta H. So if you know the individual delta H values, then you can add them up and come up with the overall delta H. So let's get a definition down for the Hess's law. And so what we want to say here is that the heat, remember we're talking about energy here, but the heat of a reaction, so the heat of a reaction, and that would normally be a delta H, and you might want to put that in parentheses like this, delta H. The heat of a reaction is constant, meaning that it's not going to change. So like if we're looking for what happens with hydrogen and oxygen making water, it's always going to be the same value. Heat of the reaction is constant. There we go. Gonna kind of tight space here. Heat of the reaction is constant whether it's going to be carried out in one step or multiple steps. And so let's write that here. Whether it is carried out in one step or multiple. So what this is telling you is that the path doesn't matter. It's just the end result. So the path is not important. It's the end result. So if you look at these graphics here, you can look at these various steps. And so if we're here and we're going to go here, if we go in one step, then the answer of delta H would be delta H3 because it's the difference from here to here. And so that value would be your delta H. Or we could do it in two steps. We go from here to here, and then we go from here to here. So if you do it in one step or you do it in two steps, the answer is going to be the same. So let me just put some fake numbers on here. Let's say that this is 50 kilojoules. So we'll say delta H3 is 50 kilojoules. All right, we're just making that up, right? We can look these up, but I'm just making this up at this point. Well, let's say delta H1 is, let's just make it 10 kilojoules. Well, delta H2 would be 40 kilojoules because see these two things are covering the same distance, and so they're going to have the same delta H as this one here that covered that same distance. And so over here, this is two steps, but the answer is still the same versus over here, which is only one step. And so that's sort of the idea. So you could go 50 steps or one, and at the end, the answer is going to be the same. And so we see this in this unit where a lot of what we do is find delta H, find delta H, find delta H. Well, if you do it with 6 different ways, the answers will all be very similar. Now, sometimes based upon our charts and our math, you see some slight variations, like, plus or minus a few kilojoules, but at the end, it's pretty much the same. So here's the same idea. So I could jump across here, go from my reactants to my products. And so that would be a single step. And so you would have this value, or you could go in this direction here to here. Now, if you go this way, this will become plus 1, 3, 6, 7. So if you take these two values and you look at them, you're going to get negative 277, or pretty close. So let's just do that in our calculator real quick. Let's go negative 1646, and then add 1, 3, 6, 7, and I got negative 279. So like I said, really, really, really close. So if I went in this direction, I went from here and then to here, it's negative 279 based upon these values. Well, that's pretty much the same thing. So it's this way or it's this way, and you're getting the same answers. Now, I do think that it's probably important to point out that we have a we have directional arrows here, and so this arrow going this direction like this, if we flip that, then we just take our delta H and we also flip it. We saw that in the last set of notes. So if I go this way, suddenly it's plus 1, 3, 6, 7. And then if we want to make this the product here, I could go here like that, one step, so negative 1, 6, 4, 6. Or I could do 2 steps, and I could go this direction. I could go to this chemical first, and then slide down this way. Okay, so then I would just follow the arrows. So I would take negative 277 plus negative 1, 3, 6, 7. So let's do that. Let's see if we get something that compares to what they could do in a single arrow. Okay, so here we go. Negative 277 plus negative 1, 3, 6, 7. And there we go. I got 1, 6, 4. Whoops, forgot my 1. 1, 6, 4, 4. Well, once again, pretty darn similar. And so that's the idea. Multiple steps or a single step is going to land you in the same place. So that's the general idea of Hess's law. Okay, now in practice, we got to be